Okay, hi everyone. It's quarter past the hour at 6:15 in the morning where I am, so I'd like this to be quick. It's also winter, so I'm nicely bundled up and remembering happier times visiting Arizona at this time of year. So I'm going to give a brief introduction to this workshop. I'll start now, will be recorded if people miss this. I'm going to take slightly more than the 2 minutes I allotted to myself, but I'm also the timekeeper, so that's okay, but nobody else gets this privilege. So bear that in mind. That was mainly because I wrote my slides and realized that I needed to tell you slightly more. So let's start by myself sharing and pressing the right buttons. So this is the low surface brightness astronomy with LSST workshop. This was proposed by myself with Aaron Watkins and Lee Kelvin to have this discussion at the PCW this year. So we're really inspired by the depth of images like this from hypersuprime ultra deep area. This will reach similar depths to LSST's 10-year depths. And you can see that a lovely low surface brightness or fuzzy light that you can see around all of the galaxies in this image. So a quick introduction to the workshop. Timing will be by me. Chat monitoring will be by Lee Kelvin, and notes will be taken by Aaron to present at the final summary breakout session on Friday. Questions will not be asked after each talk. They'll be asked in Slack, please. And with a discussion at the end of the time. So if you have questions you'd like to ask in a more open forum or discussions about the subject, we've left a good chunk of time for that at the end, even with my slight time grab. There is a code of conduct for this meeting. Please be thoughtful of one another is what it summarizes to. So be good to each other. So I also really wanted to use this time to introduce those of you who aren't members to the Low Surface Brightness Working Group. So this is part of the Galaxies Science Collaboration. It's co-chaired by myself and Aaron Watkins at the University of Hertfordshire. We have a web page. I realize these always go past very fast, so the slides will get uploaded. They are recorded, and also I'm hoping that I've written it down small enough that you might be able to grab it and take a look in this moment as well. We also have a Slack channel, so that hashtag galaxies-LSB and the LSST Slack is ours. And we meet bi-monthly, and for the last year or so, a little bit more, we've run 4 challenges trying to understand the low surface brightness universe in the context of wanting to get going as quickly as possible once LSST is available, data is available to us. So those 4 challenges are not going to go. So how well do Rubin algorithms deal with the low surface brightness light? That's being led by Aaron Watkins, and that has its own Slack channel, LSB-Challenge 1. How best to calculate distances to those galaxies, led by Harry Ferguson, and that's challenge 2. Do observers and simulators see the same intracluster light, being led by Maria Montes, challenge 3, and which low surface brightness tidal features constrain theory in, again, that context of an LSST depth image, being led by Gareth Martin, and that's the 4th challenge. So I've got quick updates from the challenge leaders. Apart from, I do have to apologize. Oh, I'm going forwards rather than backwards. Apart from Harry Ferguson, due to my being incapable of accessing Google Docs on occasion, which has got me this time. So how well do algorithms deal with low surface brightness light? The headline for this is, at the moment, we've been comparing injected model galaxies, so injected into the Rubin data reduction runs where they're testing the process, and we're comparing those with the original galaxies. And we're finding at the moment that flux is still being removed by the sky subtraction algorithm, where the plot on the right-hand side shows the average surface brightness in the on the y-axis and the difference in surface brightness between the processed and the original galaxies on the x-axis. And you can see that by about 28 magnitudes per square arc second, there's about a 0.5 magnitudes per square arc second difference at the moment. So that's roughly the ICL low mass dwarf regime. So it's of interest to a lot. It's not just a niche science area. This will impact more than just our science. So this is something that we're focusing on at the moment. Do observers and simulators see the same intracluster light? We've established a set of experienced ICL observers and simulators. We're generating a mock image to send to observers to see what they measure in the mock image, and having simulators make more mock images, different simulations, and tell us as observers the amount of true ICL they measure. And then we plan to use the magic of collaboration and scientific analysis to determine the correct amount. What is the best way to measure intracluster light, which hasn't been something that has been established so far. And which low surface brightness features constrain theory. Working group members have visually classified tidal features around New Horizons simulated galaxies. We find, so the plot on the right shows redshift and the flux detected in the outer regions of the galaxies down to different surface brightness depths, and lower mass galaxies are unlikely to have detectable tidal features at LSST surface brightness limits. A large fraction of flux in more massive galaxies is likely to be detected. And the number of galaxies with detectable tidal features falls with redshift. So less than 10% flux in halos of Milky Way galaxies is detected by a redshift of 0.2. So there's much more work to do. That's just a real whiz through kind of our current foci. We know that there are overlaps in interest, particularly with DESC, and we know there are more people attending here than are part of our working group. So we really welcome more members and working together with other groups with mutual interest to maximize our mutual outcomes. And please contact Aaron Watkins and myself if you are interested. And with that, it's on to the workshop. And our first speaker was, and I can't remember which order I did this in, whether it was Lee or Aaron. I can see Lee. Can you wave if you were first? You were first. Excellent. Thanks, Lee. I can't hear you though. I'll stop sharing. That helps. Still can't hear you, Lee.
Okay, apologies. Yes. Can you hear me now?
Yes, can hear you now.
I've had to switch to an alternative medium. Something's wrong with my Zoom. But you'll be able to share my slides, Sarah, and I put them on the website.
Yes.
Thank you
give me 1 second.
Sorry for the last minute changes, but I'm having some Zoom issues today, apparently.
Okay, excellent. So we've got just, yeah, there we go. Download. Okay, let's go share screen. No. No. Okay.
Wonderful. Thank you so much. All right. Hello, everybody. Sorry for that slight delay. My name is Lee Kelvin. I'm a member of the DM team here at Princeton. I just want to give you a very quick introduction to the data processing pipeline, specifically with regards to LSB science, how it interplays with some of the LSB goals. Next slide, please.
A minute. It's saying shared is pause, bring shared window to the front. Which window is on the front? Okay. Does that work?
I don't see anything from my side.
I could share the slides if that would help.
It might help. Sorry, I've got it in front of me and it's saying sharing is paused and it's not telling me when I press resume, nothing happens.
Can you leave full screen?
Yeah, that might help. Stop sharing.
Lee, do you want me to
Yes,
share from the Google Doc?
If possible, thank you so much.
Will do.
So in an attempt to fill the dead air, apologies again. So I'll just say that I want to talk about the science pipelines, give a very quick overview of how the science pipelines work, how we process imaging and data, and what impacts that has on LSB science.
There's me trying again. Does that work?
Yes, I can see slides transitioning, so that looks good. Thank you very much. Okay, great. So yes, so as a very quick intro, this is a very nice high-level plot that shows how the science pipelines play with inputs and produce outputs. So a whole bunch of input data go into the science pipelines, commonly referred to as the stack. So if I use the phrase stack, that's what I'm talking about. The stack is just a collection of tasks and functions that process all these images and produce various outputs. Along the bottom row here, you can see some of these outputs. We have images, single visit images, co-added images, and also a whole bunch of catalog data. Next slide, please. Okay, so images and catalogs, processed visit images are the official name for the single frame outputs. These are also referred to as CalExps, or calibrated exposures. We also have co-added images, deep coads and deep coad CalExps, which I'll talk about later, and then a whole bunch of additional models. So you can see, for example, PSF models, which are very useful for some of your modeling efforts. There's also a number of tables that are output, source tables. So sources are single visit objects, things that are only detected in a single band, for example. And then when we combine all of that information at the object coad level, we call these objects. We have object tables as well. Okay, next slide, please. Right, so the very first step is single frame processing. So on the left here, you can see some raw data for a Hypers PrimeCam image. This is a G-band image, one of the detectors in HSC. It's one of the regularly processed data sets that we push through the science pipelines. And the very first thing we do is construct a post-ISR CCD. So we construct the detector, we remove, generate flats and biases and things like that, do crosstalk correction and so on. And then on the very right-hand side, you can see the CalExp. So here we do the final single frame tasks such as background subtraction, source detection, deblending, point spread function estimation, and so on. Next slide, please. And then you end up with this lovely full focal plane image. If you look for all the detectors here, again, this is Hypers PrimeCam. You can see the full focal plane, which looks very nice. Next slide, please. Okay, so as an aside, so with Hypers PrimeCam, one of the early issues we observed was a certain amount of over subtraction surrounding bright sources. So on the left here, you can see the public data release 1 image this is from Ahara et al. 2019. This is particularly important for LSB science because over subtraction around bright sources directly influences your ability to measure, for example, the stellar halo, or indeed any LSB objects nearby this bright source. For PDR2 and onwards, a solution was developed which constructed this lovely image on the right-hand side, which resolved much of this issue. Next slide, please. So you can see the solution that was arrived at was to generate a full focal plane sky solution. So instead of the single detector background just shown in the middle here, we have on the right hand side a background that uses the whole focal plane information to generate this sky solution. And so when you apply that as a kind of additional correction, then you end up removing much of this over subtraction surrounding bright sources. So it works really well. It's just one example of one of the tasks we've used to focus on LSB science. Next slide, please. Okay, so then warping and stacking happens to produce co-added images. So the visits are all warped to the dimensions of the tract and patch of interest, and then those visits are combined to produce co-add outputs, which is what you see here. Deep coads are probably the most appropriate data type for LSB science. There is an additional deep coad calyx data product output, which is another sky subtraction happens thereafter. However, for LSB science, we recommend not using those and limiting yourself to these data products, which is typically more useful for LSB science. You don't want that additional aggressive sky subtraction that happens thereafter. Next slide, please. All right, so a couple of asides about some useful things that exist in stack outputs. So sky sources and sky objects. These are pseudo objects that are placed, pseudo randomly placed in each detector and on each co-added image at locations where no other objects exist. So we look at all the detection footprints for all the objects that are being put in the frame, and we then use that information to drop 100 sources or objects onto each, onto these images, essentially in empty patches of sky. And all those sky objects, the sky source data exist in the output catalogs. This is potentially very interesting for LSB science because you now have a measure of flux all across the image, essentially measuring your background or your sky. So it should be very useful for certain LSB QA analyses or for any kind of robustness checks into your sky solution, for example. So that's just one example of something that exists in Stack you may want to have a look at. Next slide, please. With the mind towards the future, something we've been doing a lot of in recent months, again, working with Aaron and the LSB UK Low Surface Brightness Working Group, is injecting synthetic sources into our imaging and then pushing those through the entire stack processing and looking at the outputs. So having synthetic sources is really useful because we know the truth, we know the true value, which means that we're then able to look at the outputs and compare them to the known inputs to see how our images are being processed and where we're making some mistakes. So here you can see an example on the left of a recent run where we injected a few fake sources here and how that's modified the detection footprint in the very bottom left corner. The central plot shows a classic trumpet plot. So it's your delta magnitude on the y-axis as a function of magnitude. You can see how the input compares to the output in terms of total magnitude estimate. And on the right-hand side, this is a kind of different variation on the plot that Sarah just showed in her slides earlier. We're looking at the surface brightness at which the known surface brightness profile deviates by more than 10%. It's a plot from Aaron. And we're hoping to start generating metrics like this on a very regular basis to help ascertain how well we're doing at estimating the sky. Okay, next slide, please. So final thoughts are, this is the full pipeline for Hypers PrimeCam. The pipeline's a little bit different for each survey. Some require different processing steps than others. But nevertheless, there's a lot going on, and we're constantly working to try and improve how we do things, particularly with a mind towards LSB science. And if you do need more information, you can visit that link at the bottom there. All of the documentation for the pipelines is there. And of course, you're always free to message me or any other member of the DM team, and we'll be happy to get back to you. And that's it. Thank you.
That's great. Thank you, Lee, for that great oversight of the DM team's hard work on these pipelines. Like I said, we'll keep rushing through, and we'll have questions. If you've got questions for Lee, please put them on the Slack page, and he'll kind of get on to answering those. And in the meantime, we'll have Aaron Watkins. Aaron, do you want me to share your slides, or do you want to do that? I've got them here, so I can.
I can risk trying it myself real quick. Let's see.
Most people in the world are less incompetent than I am about technology. Excellent.
You know, it changes every time. Okay, let me just get into, if it'll let me, presenter mode. How does that look?
That's perfect. I'll give you an 8-minute warning if you like, a 2-minute warning to go if you get there.
Okay, sounds good. I'll try to go quickly. Okay, so I thought after Lee's talk, it would be good to go over some of the early work that I've started doing with sort of a variation on the sky subtraction routine to try to fix some of the problems that we've identified. So that's what I'll be talking about here. Just as a quick summary, a bit more detail. I know we keep bringing this up, but we've done some work doing model injections in the pipeline already. And what we found more or less is that the models are influencing the sky that's being subtracted locally to them. So you can see that on the left plot here. This is showing the loss of flux normalized by the model size as a function of model brightness. So in an ideal world, you wouldn't see any trend in this because the model shouldn't be influencing the sky that's subtracted, but you can see that there's this positive gradient where the brighter the model, the more sky per unit area is actually being subtracted. So evidently they're influencing that to some degree, which you don't want. And then also, as Sarah already showed, low surface brightness stuff is getting subtracted more than high surface brightness. So for the average model, at about the 26 mag per square second isophote, we're losing around 10% of the flux. By 28, it's about a half a magnitude. And then as you get to very faint surface brightnesses, we're losing basically all of it. So it looks a little like that HSC PDR1 issue that Lee already showed. So in general, we can conclude from this that the sky subtraction algorithm is not doing very well for LSB flux at the moment. And so we'd like to adjust it so it does better. What exactly is going on? It seems to be that a similar sort of issue is happening as was happening in PDR1, but although again, it's not nearly as bad as it was, it took this level of detailed analysis to even identify that this was happening. But the basic issue in that case was that the sky that was being subtracted was measured a bit too locally and was incorporating, probably because of the complexity of the sky model, it was overfitting and incorporating the wings of extended objects into the sky local to them, which you obviously don't want to happen. So most LSB people have settled on using very low order fits to the sky to get around that issue. You do a lot of masking and then you fit the sky as either just a number, a flat sky, or if you have to, you go up to maybe a plane, but nothing really higher than that. That gets dangerous at that point. That's a good strategy for a lot of projects, but unfortunately, sometimes that just doesn't work. For example, in really red bands, the sky shows a lot of complex structure that's just not well fit by a plane. And also with survey data, like with LSST, you're going to have a lot of images that are taken with the moon out or near bright sources like planets, naked eye stars, things like that. Maybe you'll take some images with light cloud cover. And the other issue is that Rubin Observatory, the telescope in there, I think is an open tube design. So you get a lot of this light scattering around more than you would, for example, with a closed tube type telescope, which leads to a lot of structure on your images. So what you really want in this case is some kind of a sky subtraction algorithm that is able to accurately remove even complex night sky foregrounds without over modeling or over subtracting actual astrophysical flux. So these are the very first steps of trying to come up with an algorithm that does that. I've been developing this using whatever data I happen to have on hand. Primarily, I've been using Nordic optical telescope data because this is for a thesis project with a student I'm working with, Vigurautio at the University of Oulu. This was taken on a public telescope, so we had the conditions that we were given. We just had to take data during those conditions, and a lot of those were not ideal, which means we have some very complex structure in our night sky foregrounds. So that makes it a pretty good test case. But in addition to that, I've so far also tested it on some older data I had from my thesis days with the Burrell-Schmidt telescope, This is a telescope that's actually outfitted for LSB science. So it was engineered to do LSB science. So the night skies are actually very well behaved in those images. But there was one galaxy that we targeted that was in a field that was full of galactic cirrus, which was M64. So I wanted to see, does this method also work when there's not terrible night sky contamination, scattered light, but astrophysical contamination, low surface brightness, astrophysical flux that you obviously can't get rid of with your observing strategy. The goal is to do this on a lot of other data sets. I've begun doing it on a couple of others. The ultimate goal here is to try to get it working on HSC data, because that's what we're going to end up with, in the LSST era. So the basic method is actually pretty simple in concept. I believe it was Yusra and Robert at the DM team who originally came up with the idea. And I've just decided to try it out to see if it would work. What you do is you start off with a preliminary image coad that's sky subtracted. You can see an example of that on the left here. All you need is an average zero count background without any kind of large scale residual structures. So no planes or cosmic ray hits or reflection donuts or anything like that. Because you then take that coad and you align it with your individual images, crop it to the right dimensions and so on. And so as long as it has an average zero background, you can scale the flux on that coad to the flux in the image and then subtract the coad off, which removes all of the astrophysical flux and leaves behind a kind of rough map of the night sky in that individual frame. Of course, it's nasty, it's very noisy. Everything that's not in the coad, like all these cosmic ray hits, those get left behind. Differences in the PSF can leave behind artifacts around point sources and so forth. So this is more of a starting point. The tricky part is taking that starting point and processing it in such a way that you can actually use it as a night sky map. So in my preliminary attempts here, I just did something fairly crude. I just masked out all of those artifacts I mentioned, binned the heck out of the image to get the noise down. If there were any residual masks left over on the binned image, I just interpolated the flux across the masks. And then because it looked very blocky and I wanted more of a smooth map to interpolate that a little better, I just applied a Gaussian filter across the whole thing, which leaves an image that looks like this, which you can see traces the overall pattern of the night sky fairly well. And even with this relatively crude processing, which results in kind of a low resolution, but much less noisy map of the night sky, you end up with an image like you see on the right when you subtract that off, which has a nice clean background, which was why I decided to pursue this in the first place, that it looked that good, even with this kind of rough attempt at this. It also looked way better than what we were doing before, which was to fit the night sky as a second order polynomial fit to all the unmasked pixels in the frame. So this on the left here is showing a sky subtracted image. So this does have a mean background of 0, but you can see all of this residual stuff left over at large angular scales, whereas the right image is showing a sky subtracted image using the method I just described, and you can see immediately that it does a much better job. But of course, the real question is, does it preserve flux? So I've started testing this using some model injections here as well. In this case, I just built a model of the target galaxy. I just fit an exponential to the thin disk of that galaxy, and then using GalSim injected a model just to the east of the galaxy in every frame just prior to sky subtraction. So we create a coad with the model present, we create a coad without the model present, and if you subtract the latter from the former, you end up with just the model plus any kind of differences in the sky subtraction induced by the presence of the model, which is what you're seeing on the right here. I've scaled this such that all of these things are visible, but all of these divots and other things are actually at a very low level, a few orders of magnitude below the actual noise limit of the coad. So the global sky is not being influenced by the presence of the model much at all. Local to the model, though, is what we're more curious about. So to test that, I've just done surface photometry of the model in both coads, the H alpha and the R band, which I'm showing on the left here. The ground truth is shown as the black line. The surface brightness profiles on the H alpha coad and the R band post sky subtraction, of course, are shown as the two red lines. And I'm showing the curve of growth, which the total enclosed magnitude is a function of radius on the right. The bottom two plots are showing the differences between the red curves and the ground truth. And the long and short here is that while it's not perfect, we are seeing a bit of under subtraction in the outskirts. It's behaving pretty well, and it's behaving a lot better than what we were seeing with the LSST pipeline so far, where we're getting maximum deviations down to a very low limit of, maybe 5% or so. And also the curve of growth, the total integrated magnitude, while it's a bit off in the center, we're getting back the total magnitude to within, much less than 1% precision in that case. So again, this is very preliminary. This is just me fiddling around trying to get this to work. And even with that level of effort, we're already at a pretty good spot. So I would say that's pretty encouraging. As I mentioned, though, I wanted to test this in a field with a lot of galactic cirrus contamination. So I had these images of M64. I'm showing you the coad of that we published in 2016 on the left here. Here's the galaxy, and you can see all this lovely galactic cirrus all over the frame. So I did the same kind of experiment. I just injected a handful of models. In this case, just for fun, I used some really low surface brightness kind of models and injected them around the main galaxy, and then did the same sort of analysis. So this is showing the global sky subtraction as it's altered by the presence of the models. And in this case, I think because they're so faint and because they're so small compared to the field of view, the impact on the global sky is negligible. It's almost 40 mags per square second equivalent. So again, that's a good sign. And local to the models, we're seeing similar sorts of offsets as we saw with that edge-on model that I showed previously. In general, we're sticking pretty close to very low offsets, and at maximum, again, mostly in the center for reasons I can explain during the Q&A, we're getting maybe a maximum about a 5% offset, only down to extremely low surface brightness, almost 33 mags per square arc second, are we starting to see about a 10% systematic offset in surface brightness among all of the models that I injected. So it's essentially stable to within about 10% down to much lower than LSST is ever going to be capable of achieving, which again, given how crude this early effort is, I think is a pretty good sign. And this is okay, I'm almost done. So given all that, given that this seems to also work in fields with pretty heavy contamination from galactic cirrus, I think this is a pretty encouraging early result. And so we're going to push forward with this method and see if we can get this working on HSC data to better precision, see if we can fix some of these offsets that we're already seeing and get this working for LSST. So that's basically all I have. If we do get it working properly, I think it also has application beyond LSST. For example, infrared imaging, it has notoriously difficult to model skies. So I can see something like this being useful for other kinds of imaging as well. So yeah, put your questions in Slack if you've got any thoughts about this. If you have any comments, I would be very interested in hearing about it.
That's great. Thank you very much for that, Aaron. Like Aaron says, please dive on him in Slack. Lots of questions, I'm sure, and comments, but this is really exciting work for our field. We'll now dive into the part of our workshop where we're just trying to get a taste of kind of some of the projects that people are working on at the moment. So really quick talks. I know some people have uploaded their slides. I've grabbed those, but not everybody has. So we'll kind of just go to each person. And if you want me to share, I've got them. Otherwise, you should share away. So I know Cristina Martinez Lombia is the first speaker. And I think we'll do if you get kind of, 10 seconds away, 15, 20 seconds away from 2 minutes, I'll jump in and say something. And that's
okay.
Please say your last word.
Okay, I'm gonna try to share my screen. Okay, can you see my slide?
Yes.
I can see your background.
No, we
I
see
can
it
see
now.
slides now. Excellent.
Okay, great. So hi, I'm Cristina Martinez Lombilla, and I'm going to show the first detection of intragroup light in the HSC data registry. The intragroup light is composed by stars unbound from their host galaxy due to interactions, so it is basically a fossil record of the interactions a system has undergone. However, it is very faint and very hard to detect. Here you have the reduced data of the image of our group of galaxies, where we have developed a method to detect and analyze this intergroup light. We have done it in the most automatic way up to the date, and we reached a software brightness limit of more than 30 magnitudes per second squared in the I band. This is equivalent to the LSST 10-year depth. We perform also a PSF correction over the brightest stars and in the field, and also on the galaxies of the group to avoid an overestimation of the intergroup light, but also any incorrect color measurements. This is the results after subtracting the 3 brightest stars in the field. Here we use a very extended HCC PSF, so you can see how a very faint component is removed, but preserving the intergroup light. We then perform a 2D model of the galaxies in the system, accounting for the intergroup light and also convolving them with this PSF. By subtracting the group galaxies here, we get this beautiful image of our IGL. And zooming in here, it is clear how the IGL has been preserved, and also that the residuals from the galaxies are minimal. So what we did was to extract a radial software brightness profile with a reliable detection of the IGL up to 140 kiloparsecs. We are currently working on further analysis and improvements of the method. However, these results are promising and are an example of a post-PSF treatment in case the Rabin Observatory do not provide a dedicated PSF. So this is all on my side. Please keep a look on the upcoming paper. Thank you so much.
2 minutes, perfectly. If you can stop sharing, and we'll have Mike Rich. Mike, do you want me to share, or do you want to share? Excellent. Mike, I don't know if you're muted, but I can't hear you.
Yes, I'm muted. Thank
Great.
you. Okay, thank you. Yes, this is the Heron Survey, and here are the collaborators. This is taking place with 2 Centurion 28-inch telescopes at Wise Observatory and one near Fraser Park, California, and there's an 18-inch telescope in commissioning. This is a picture of the telescopes that have been praised. The quality of the images have been praised by Javi Roman. This shows the first paper, which was 119 galaxies. It's a data archive with all of our data, and notice that we go very faint, as faint as the CFHT in the same time for low surface brightness specters near NGC 147. We found a correlation between the envelope diameter and size and the absolute magnitude of the galaxy. This result was one of the deepest ground-based images of the group. This was the NGC 1052 group composed by Javi Roman, and this goes to about 31 magnitudes per square arc second. You see lots of tidal structure in this image. And here are some other papers that will be available in the PDF that I'll upload shortly. We're doing 2 ongoing projects, one in which we image, this is led by Jonah Gannon, where we image ultra-faint dwarf galaxies, which are followed up by KCWI at Keck. The second project, which is our major effort, we're doing roughly 50 to 100 hours on NGC 4258, 5907, 7331. We're doing H alpha and broadband imaging with
15 seconds to go
to detect extranuclear H alpha. Thank you, and that's it. So that's our main program, is extranuclear H alpha this time.
Thanks, Mike. Next we have Innocenza Busa. Do you want me to share, or do you want to? Okay, you're still muted, so. Excellent. Can't hear you still. Yes, I think I can hear something. No, overexcitement, I can't.
I think I'm not hearing anything either.
You're still muted.
Can you hear me?
Yes.
Yes. Good morning. I will talk about the challenge of LSST to shed light on the origin of galactic cosmic rays. Cosmic rays are charged particles at a relativistic velocity. Observing them from Earth, we cannot directly derive where they come from because they are deviated by magnetic fields. Recent observations have shown suggested the presence of unidentified source of cosmic rays at a distance of a few kiloparsec from the solar system. Candidates are strong wind and outburst, typical of luminous blue variables and Wolf-Rayet stars, and magnetic reconnection from flare and magnetic chemically peculiar stars. LSST has the capabilities to solve the long-standing problem of galactic cosmic rays origin by detecting in loco effect due to the passage of cosmic ray through diffuse region close to candidates. These local effects are evident in supernova, are observed in supernova remnants. Here an example of VST image where H alpha and red filter are superimposed. Some filaments show flux enhancements that can be seen from counts averaged on this slit. You can see that red filter counts can detected, indicating the capability of LSST of detecting the phenomenon.
15 seconds.
The flux enhancements are connected with the passage of cosmic rays, as shown from spectroscopy along the slit. We obtain a wide H alpha profile that can be explained by charge exchange between shock protons, accelerated protons, and the steady hydrogen of the diffuse regions. We are now working on archive images to evaluate physical and geometrical constraints, and we are beginning testing on the simulated images of DDP0, and future work will be on the automatic detection of diffuse regions and sources.
Okay, thank you. Let's move to Raphael Shirley, please.
Hello, I'm going to share my own screen.
Thank you.
Hello, yes, my name is Raphael Shirley. I'm a postdoc at the University of Southampton in the UK, working on the UK in-kind contribution. And we're working on joint processing of Rubin optical and Vista near-infrared imaging. So here's the Vista telescope here. I'm sure lots of you are familiar with it. It's a 4-meter telescope, 1.65 degree square field of view. It has the ZYJHKS band. So the crucial thing is it extends this coverage to JHKS, and the Vista Hemisphere survey covers 20,000 square degrees, so more or less covers the entirety of the wide, fast, deep survey. So I think for objects that are detected in the near infrared in this Vista imaging, this will add extra information for instance, photometric redshifts, and also for particularly red objects. So in the bottom right here, there's an example of a coma cluster progenitor where the Vista near infrared imaging is giving you extra information in addition to things like high redshift quasar candidates. And we're processing it through the LSST science pipeline. So the idea is we have an additional set of images on the same pixel scale. So any one of these so-called patches in LSST, there'll be Vista imaging there available. And we've produced this test data set over 800 square degrees, overlapping with Hypersphere PrimeCam. Like everybody, we're using Hypersphere PrimeCam as the test. And yeah, we're working on sort of quality control on that data set now. So if you're interested in this data set, please get in touch. We're very keen for people to be using this for science purposes. And yeah, we're particularly interested in the discussion today about sky subtraction. The sky in the near infrared is large and very quickly varying. So the advances discussed today are very interesting to us. And all the code is public, so please get in contact with us if you want to have a look at it. Thanks very much. That's everything.
Perfectly timed. Thank you. Let's go to our next speaker, who's Chris Usher, please.
Hello, I'll share my own screen, please.
Go for it.
So with its unprecedented survey volume, depth, number of photometric bands, LSST is going to image, detect, and study an immense number of extragalactic globular clusters. Back of the envelope estimation, about 1 million. I sort of illustrated what we could do is this is a image from the slug survey using a super much shallower image than what LSST is going to provide in fewer filters. And we were able to find nearly or over 6,000 globular clusters around this brightest group galaxy, which is infalling into Virgo. In our current understanding of how star clusters form and evolve, there's a very close link between the properties of the star clusters and the assembly and formation history of the galaxy. So if we can measure the number of globular clusters, their masses, their ages, their metallicities, we can learn something about the progenitors of various low surface brightness features, be they dwarf galaxies, galaxy halos, the intercluster light streams. Because LSST is going to provide ages, metallicities, and masses for a huge number of globular clusters. I'm going to talk a bit about that tomorrow during the research bites. But an example of the extra information that globular clusters can provide. So this is an image from the PANDA survey of streams and other low surface brightness around M31, where the grayscale is the stellar density, and then the colored points are individual globular clusters that were found in the halo. And you see that they're associated with the number of the streams. And
15 seconds.
Brightness of these globular clusters allows them to be followed up in a way that you typically can't for the low surface brightness light. And in this case, able to get spectroscopy and the radial velocity of these streams from their associated globular clusters, allowing to map out how these streams are moving around the host galaxy, which is something that typically you wouldn't be able to do otherwise. And this is something that you can do for much more distant galaxies with available spectroscopy today. Thanks.
Great. Thank you, Chris. Let's move on. We'll have Ryan Jackson next, please.
Hi, I'll try to share my own screen.
And I'll just a quick, Louise is having some Zoom connection issues, so I pushed her talk to the end. So whoever was before Louise, don't use that as a marker anymore.
Can you see the slide?
Yes, and I can hear you.
Great. Hi, so I'm Ryan Jackson. I'm going to talk about the origin of low surface brightness dwarf galaxies. So our statistical understanding of galaxy evolution is driven by objects that are brighter than the surface brightness limits of the current wide area surveys. And it's therefore largely restricted to relatively bright galaxies. But both theory and observational work have started to indicate that there are probably many galaxies that are fainter than these surface brightness limits, especially at the low mass end. So in order to study these galaxies, we use the hydrodynamical cosmological simulation New Horizon, which has a stellar mass resolution of 10 to the 4 solar masses and a maximum spatial resolution of 40 parsecs, making it an ideal tool for investigating the evolution of dwarf galaxies. So in this study, we explained 1, how low surface brightness dwarf galaxies formed, and 2, why at a given stellar mass do dwarfs have a large range in surface brightness. As you can see from the plot on the right, we find that New Horizon galaxies populate a well-defined locus in the surface brightness stellar mass plane, in agreement with deep SDSS Stripe 82 data. So we found that at a given stellar mass, galaxies with fainter surface brightnesses today are born in regions of higher dark matter density. This results in faster gas accretion and more intense star formation at early epochs. The stronger resultant supernova feedback flattens gas profiles in these galaxies at a faster rate, and that results in shallower stellar profiles. As star formation declines towards late epochs, the tidal perturbations and ram pressure experienced by these systems accelerates the divergence in surface brightness and increases their effective radii and reduces star formation. We found that a small minority of dwarfs depart from this main locus towards higher surface brightnesses that would make them detectable in past-wide area surveys. So it's an important prediction that these galaxies that you see now are not actually representative of the total dwarf population. And they were formed by flyby or a recent merger event. We also found that ultra-diffuse galaxies, which some consider to be extreme or anomalous, actually dominated the dwarf galaxy population. And so we predict that ultra-diffuse galaxies should be routinely visible in future surveys like LSST. Thanks for listening.
Thanks, Ryan. Let's have Louise is here. Let's have Louise up next, please. Thank you.
Hi, thank you. I am having some internet issue turn-offs that helps. So I'm going to be talking about brightest cluster galaxies and intracluster light and some work we've done looking at those two together. Here's an SDSS image of a local brightest cluster galaxy and our field of view that we use in this project, which is a spectroscopic project using the SPARSE-PAC instrument on the WIN telescope. Is highlighted here. Now, certainly we're not looking at all the ICL spectroscopically, but Worldster Light kind of starts to take over from the brightest cluster galaxy. So what we do is we add up the light from all of these fibers in different regions surrounding the core of the brightest cluster galaxy, and then we model these spectra in order to find the best fit of age and metallicity in 23 systems, 23 local systems. So what we found that supports lots of other work, including that by Maria, but we've looked at this spectroscopically for a sample of local systems, is that the core of the brightest cluster galaxy is dominated by these very old, high metallicity stars, which has been seen for a long time. But we're also able to look out at the intracluster light and look at the share of stellar populations. And we can see that the young populations, which for us means like 8 gigayears instead of 12 gigayears, the young stellar populations are more light than the BCG core itself. So Rubin is going to allow us to go deeper and also to look for connections between the BCG, the ICL, and the superclusters. So the galaxies and the filaments, for example, in terms of their orientations, their shapes, the stellar populations. And I've been having fun with DP0, looking at a cluster there and using some adaptive kernel techniques to look at the large structure. And that's kind of what I plan to do in my new involvement with Rubin using the DP0.
Thanks, Louise. Let's have Bene up next, please.
Screen. Okay, here. All right, small but mighty. The possibility of using TESS, the Transiting Exoplanet Survey Satellite, for LSB observations. So this is not about LSST, but something where we have the data in hand already. So TESS has been taking a pretty big chunk of the whole sky for to look for transients in the brighter stars. And so this is what's been covered so far. Some of the sectors had to be moved up, but a lot of the sky has been imaged in 30-minute cadence. But the thing that struck me, so for example, you can, is that the ecliptic poles have been imaged for the entire half of the TESS mission. So this is 351 days of integration. And so there are galaxies in there. So if you really want an LSB challenge, you can go see if we can fish any more information out of this. So you can get two things from this. One, it's sort of resolves M51 here, if you recognize it. And then secondly is that there are the PSF is pretty big, and there's still some striping happening because that's where the CCD was glued. So just looking at the 27 days, which is the normal integrated time for tests to look at any given part of the sky, and the 351 days. 351 days where either of the poles have been looking. That means you can potentially hit surface brightnesses of 33 to 34, and the purple points are all the stuff that Dragonfly array has been doing. So you can look at the stellar halos in principle of nearby galaxies this way. So, and the data is in hand.
15
So
seconds.
that might be worth looking, especially let's look at some edge-on galaxies, but they don't look very photogenic at the moment. But I hope that we can actually subtract the PSF there and have a look at the global properties of some nearby galaxies. So TESS might do well as a surface brightness observatory. The exposure times will only get better. TESS is chugging along just fine. The PSF won't get any better though, so it's probably good for full stellar halo properties like ablateness, but substructures might be a lot harder to do. If you want to challenge yourself, here's TESS.
Thanks, Bennett. Let's move straight to Facundo, please.
Yes, hello. 1 second. Can you see the presentation?
Yes, I can.
Good. So today I want to tell you a little bit about the work we have done here at the University of Barcelona, with mainly done by Alex Pera Casanova, master students. The goal of the project was to use fully cosmological hydrodynamical simulation of the formation of Milky Way mass galaxies to generate basically mock LSB maps and try to identify the brightest streams or the brightest LSB features on each of these halos, right? Why? Well, we wanted to quantify the of galaxies, model galaxies that show LSB features as a function of limiting surface brightness magnitudes, understand what these brighter features are telling us about the recent accretion histories or late accretion history of the galaxies, and learn whether these events are always associated with the most recent events, and whether these brightest stream progenitors are always associated with the most significant contributors of the stellar halo of the galaxies. So what we did is to go to each of the simulations, look for these brightest streams as a function of surface brightness limit in magnitude, extract some properties of the progenitors such as infall mass and infall times, and do some statistics. So a nice result here on the right, what you're seeing is the accumulative fraction of models that shows LSB features as a function of the limiting magnitude. And what you see is that our models predict basically that if we manage to reach limiting surface brightness to 29, 45% of our models should present a bright stream. But if we manage to go a bit further to 30 up to 70% of the galaxies that we observe should show these low surface brightness features, I mean the brightest streams. In general, these brightest stream progenitors are associated with not
15 seconds.
Thank you. Not the very recent accretion events, a median time of 6 gigayears, so it's not something that just happened. And they are not typically the halos that have the most significant contribution to the stellar halos. They are sometimes more massive halos have been accreted. So I did here with some very general takeaways, and we can chat more about this over Slack.
Great. Thank you, Facundo. Thank you to all of our speakers in this session. It's been really fascinating to hear the variety of work that's been being done kind of on low surface brightness features in the lead up to kind of LSST to Ruben. Now, I had this glorious idea that we were going to have 20 minutes for discussion. Now, I completely failed to add in me taking an extra 5 minutes and the crossover times between speakers. So we are actually out of time, which I'm a little sad about. But we do have a Slack channel, and there's been lots of questions so far. And I think if people can keep going with the questions, and we'll kind of keep an eye on that and dive in and have some of the discussion there, that would be a lot of fun. And huge apologies, because I was also looking forward to a broader discussion about low surface brightness, but it has been great to hear all of the work that people have been doing. And now my cat wants to join in. So thank you, everybody. And huge. Yeah, we can have some audible clapping for all of the speakers. Thank you so much. And thank you for all of your exciting work, and look forward to seeing you on Slack and throughout the rest of the PCW this week. Okay. Thank you, everyone.
Thanks, Sarah.
Bye.
Bye.
Bye.